Okay, welcome to this week's lectures. Last week we were looking at the interstellar medium, the gas in the interstellar medium, and the different phases, and I left you with this problem to revisit the sort of normal ideal gas law that you're sure you're used to using, and recasting it in terms of this number density of particles that I introduced as the sort of traditional variable that's used in studies of the interstellar medium. So if you go to your normal PV equals nRT, where R is the universal gas constant here, so that's a constant, and N in this equation refers to the number of moles, okay, if you remember your A-level physics or chemistry or both. So if we're looking for an expression for the pressure, then you can see that it's basically the number of moles divided by a volume here. If you bring volume to the other side. Now clearly that is a sort of, looks like a number density already, okay? But it's the number of moles over the volume rather than the number of actual particles. So if we want to bring in the number of particles, which I've defined as little n here, then you need to scale up your number of moles by Avogadro's number. That's what Na is here, and I'll just give you the total number of particles in n moles, and divide by the volume. So that's then going to be the number of particles per unit volume, which is what the number density is. So you can see that now in this case, we get an equation like this, so that P equals n times the gas constant times T over Avogadro's number, where n is now the number density. So this tells us that the pressure of gas in the interstellar medium is just directly proportional to the number density of particles times the temperature. Okay. So I then asked you to just think about the case of an H2 region surrounded by a molecular cloud. Okay, so a nice pictorial example here, again from Astronomy Picture of the Day that come out every day, as the name suggests. And this one is showing a nice H2 region here. It's actually the blue light here is the ionized gas in this case. You've got the nice cluster of hot stars in the center ionizing the gas. And it'll be surrounded here by molecular gas. Now, I haven't shown you like a CO observation or anything like that, but just take it from me that all this red light here will be coming from, it's basically sort of reflected light coming out of a dusty molecular cloud. So if you just take the sort of typical densities and temperatures that I mentioned before, okay, so an H2 region, well, the H2 region and the molecular cloud will both have similar densities, up at 10 to the 10 particles per meter cubed. But the big difference is that the temperature is 10,000 Kelvin in the ionized zone in here, and only about 30 Kelvin out here. So the pressure in this ionized bubble here will be about 300 times bigger than the pressure of the surrounding molecular gas, which means that the H2 region here, the ionized gas, will be expanding over time into the surrounding molecular cloud material, okay, because it's overpressurized. And it will expand at roughly the sort of speed of sound in this hot gas, which is about 10 kilometers per second. So that's what pressure balances do. They try and even themselves out at the sound speed of the gas. Okay. So today we're going to sort of finish off the gaseous phases of the interstellar medium. And to finish that topic, we need to come back to supernova explosions. Okay, so we're just going to look a little bit more at supernova here. We've met them before, of course, when we talked about stellar evolution and the idea that a massive star will die by exploding as a supernova. We'll see another way of giving a supernova as well. And then we're going to focus more on, rather than what's the compact remnant left behind, more on what is actually ejected into space and what its effect on the interstellar medium is. Right. Oh, good. It's the trouble when you're running several classes at once. Okay. So let's look at supernova explosions. As I just mentioned, then we met these before, but there are actually two types of ways to get a supernova explosion. So the first one is, as we already talked about, okay. So this is a single massive star collapsing at the end of its life when it's run out of fuel and it's burned all its fuel up to iron in the center of the star, and then it collapses, but the outer layers get ejected, and this is leaving behind either a neutron star or a black hole, depending on the mass of the star at the time. And these are referred to as type 2s supernovae. Okay, so another little bit of nomenclature here, and it might feel like astronomers can't count to more than 2 as we go through this module. There are quite a lot of examples of 1s and 2s. We've already had population 1 and 2 in terms of stars. Here we have type 1 and 2 supernovae. Okay, so this is a Roman 2 again. Okay, so what's the other type? What's the other way you can get a supernova explosion? Well, I think I've alluded to this a little once or twice before, but stars like these extreme endpoints of stellar evolution, like the white dwarf and the neutron star, when you look at their physics in detail, I think I mentioned that they're literally held up by sort of quantum physics, really. The sort of Pauli's exclusion principle basically keeps these objects up. But there is a maximum mass above which even those quantum forces cannot hold the star up against gravity. So if you get a white dwarf star, and the maximum mass for a white dwarf star is about 1.4 solar masses. This is often referred to as the Chandrasekhar limit, but actually E.C. Stoner, after which our own physics building is named, also worked out this limit himself at the same time. But the the British publicity machine is not as good as the one from Harvard. So that 1.4 solar mass limit is, if you add any more material to a white dwarf that is already that massive, then it will explode as a supernova and basically destroy itself. We'll come across this a few times. So how do you add matter to a star? Well, we've already looked at binary systems. Okay. Now, if you've got 2 stars in a binary system that are very close together, the compact object can start accreting matter onto itself by pulling it off its neighboring star. Okay. Especially if that neighboring star swells up during its own evolution. So that sort of binary system can give rise to a different type of supernovae, and these are referred to as type 1a. Again, don't get too hung up on the names, but type 1a are basically white dwarfs pushed over the limit that explode, whereas the type 2s are just the sort of normal single massive star at the end of its life exploding. But basically, both of them give rise to the same type of supernova explosion, the same energetics. And I think I showed you this picture before. So this is the before and after of a supernova explosion. So you've got, this is again a type 2 one, so you've got the bright massive star here, and kaboom, it explodes literally the next day. So we're now more interested in not the explosion itself and what's left behind, but what happens to all that material. Like a huge amount of material can be ejected into space, tens of solar masses. What happens to that? Well, basically you've got a sort of an expanding fireball, if you like. It's very hot, and it's expanding very rapidly initially, tens of thousands of kilometers per second, actually mildly relativistic. But as that gas expands, it cools, and so you get an initial very rapid rise in the brightness. So this is a light curve again, so this is the brightness or luminosity, whichever you are. It's got magnitude on this side, luminosity on this side, as a function of time since the, since the peak there. But here's the rise up to the peak. Okay, so the explosion would happen around about here. And so initially it gets very, very bright within a few days. Okay? And I mean very bright. Okay? Increases by orders of magnitude. Okay, and then it will reach a peak brightness, and then as the gas starts to expand and cool, it will start to fade again. Okay, and you can see the different types of supernova have sort of different details on their light curve, but basically, you go up in a few days, and it takes about a year to fade away from the initial explosion. Okay, we'll come back to these again later in the module as well. And we don't often get to see supernovae up close, as it were. Well, we probably don't want to get too close to them because they could be rather dangerous. But this is a Hubble Space Telescope picture of, again, the same supernova that I showed you the before and after picture just now. So this was after about a year or so. So with HST's exquisite sort of high-resolution imaging, you could zoom in on, there used to be a star here in the middle, but now you can see this what looks like a bright sort of ring of light here, and there's some sort of strange thing emerging in the middle here. Okay, and you can even see some other things going on here. Basically, there was a supergiant star there, so very large and already losing some of its mass, ejecting some of its mass, and then the explosion went off sort of inside that. So it's basically the explosion has lit up its surroundings here. These are just two other nearby stars that were nearby. Nothing to do with the explosion. Now so this was about a year after the explosion. What we have here is a little movie of this. So this is a time sequence of HST images showing what happened, how this bright ring formed. Okay. So basically material is shooting out from the inner regions, and this pre-existing ring of material here, which had already been thrown off from the star earlier in its life, is about to be smashed into by the very fast-moving ejector from the supernova itself. So let's just watch that unfold here. You can see this is fading and expanding, but soon you'll start to see, as soon as that gas hits that existing ring, it literally lights up like a Christmas tree. Okay, and you can start to see this sort of shape in the middle here. That's it's kind of elongated because the gases are beginning to expand in the direction of least resistance, which is perpendicular to this ring here. Okay. So again, don't worry about the details. This is just to give you an idea that these supernovae are, things change in real time with supernova. The explosions happens in a few seconds, gets to its peak brightness in a few days, and then over the course of the next year or so, it basically blasts its surroundings with clouds of hot gas moving at tens of thousands of kilometers per second. So hopefully you get the idea that there's a lot of energy going on here, both in terms of light from the sort of explosion itself, all the gases being heated up, and also a lot of kinetic energy in this high-speed ejector. So where's it all coming from? Okay, well, we can estimate that for ourselves. Okay, basically, all of that, the source of all of that energy is the fact that a large amount of material in the star, once certainly for the type 2s, once that energy, once the fusion reaction stopped, then nothing was supporting the cloud, supporting the star. Gravity wins out, and it collapses down to a very small size. Okay. So if we assume that a lot of mass is collapsing down to the size of, say, a neutron star, then we can, I'll just quote the size of a neutron star to you, which is about 15 kilometers across. Okay. So a neutron star, or the event horizon of a black hole, actually, it doesn't make much difference. If you work either of them out, they're about a few tens of kilometers. So you've got, a load of mass, more mass than it is in the sun, collapsing down to the size of a small city like Leeds. Okay. So how much energy, gravitational potential energy, is released during that process? Well, we can just do a sort of rough back of the envelope dimensional argument here. If we look at the expression for gravitational potential energy, then it looks a bit like this. So you've got big G and then a mass squared here, because basically it's the same mass that's collapsing that is sort of ending up in the middle, if you know what I mean. So let's just make them sort of equal to each other. But it's the sort of size here, that the very small size. So you're collapsing down from some sort of supergiant type star down to something very compact. So at that level, it doesn't really matter how big it is you start from. It's where you end up is what's important. And if you put the numbers in, okay, so let's just take a solar mass for want of argument. Okay, I mean your neutron star or your collapsing white dwarf will also be about 1.4 solar masses. So just over a solar mass is about right. So this is just a rough calculation. Gives us just over 10 to the 46 joules. Okay. So, that's a big number. That doesn't perhaps mean very much until you compare it to something. Okay. So, as a little example for you to have a look at during the break, why don't you compare that amount of energy with the total amount of energy output in radiation from a typical galaxy in an entire year. So during the time that the supernova explosion is going up and down, how much energy is an entire galaxy worth of stars putting out? Okay. So you're going to need to make some assumptions here. How many stars in a typical galaxy? I gave you that in a previous lecture. And adopt, a luminosity for a typical star. And I think there's an obvious number to choose there. So have a go at that, put some numbers in, see what you get, and compare that to what we've just seen, the 10 to the 46 joules for a supernova explosion. Okay, have a go at that, and then we'll move on.